Larry. Thank you for your help.
No problem. We're going to have you on a hand like
All right, I think we can start. And welcome everyone to the final demo for AA274, Principles of Robotic Autonomy. Most of you are quite familiar with this class, I assume, but just to make sure that everyone is on the same page, this class provides a broad overview of the main techniques behind robot autonomy. So basically how to allow a robot or an autonomous vehicle to make decisions on its own. In particular, in this class, we cover techniques for trajectory optimization, perception, localization and mapping, decision-making, system architecting, both the mathematics of the algorithms, how to code them in the robot operating system, and finally, how to field the overall autonomy stack on a small robot that comprises some representative sensors that you may find, for example, in a self-driving car, like a LiDAR, cameras, onboard computing, and so on. So the students have been working hard throughout this class to build their own autonomy stack. And today we have the 5 best teams in this class. They're going to compete to be the yearly champion for AA274 and have their names engraved in the list of champions for this class. Particularly, the task for this year is to recover vegetables and other food items from the environment. So they have to look for these items, and they have to navigate in this mock urban environment. So they have to showcase all the skills that they have learned throughout this class. Before starting officially the competition, I would like to mention that next year, given the success of this class, we're going to launch a new class, which is going to be Advanced Robot Autonomy, where we're going to cover more advanced techniques, like, for example, learning-based control, system architecting, verification and validation, interaction with the world, like, for example, contact models and manipulating the world on top of a mobile base, and interaction with humans, how to predict the intent of humans and how use that information to plan actions that anticipate possible reactions. And of course, for the industry representatives that are here, we're still designing this class, so we would love to hear your feedback about suggestions that you have, about material we could include in the class. I mean, at the end of the day, some of the students here will be your future colleagues, so it's a way for you to let us know what type of skills you would like to have from your future colleagues. And our topic here is going to be, I think, an exciting competition, so I don't want to take other time out of the competition.
All right, thank you, Professor. So I guess to kick things off, first of all, as Marco said, the project here this year is food delivery. And we have 5 teams. Let's start with the first one, Team Centro. You can grab the microphone from Professor.
So hello everyone, we're Team Centro. We're a diverse team of students because we have actually every single one of a lot of the engineering departments here. So we have 2 CS students, 1 EE, 1 AA, and 2 MEs. And for our project, we have different modules. So we integrated lane following. So we're gonna display our robot following the lanes. We also have autonomous from tree exploration, which is the most risky thing that we are trying, and we're actually trying it at the very beginning. And I'm going to explain how that looks like. And we also have a camera that obviously detects objects. And what else? Camera bounding box. Oh, yeah, so that's the camera that detects the objects, and you will not be able to see it, but as we detect objects, you're going to be able to see frames being thrown. So we are going to tell you where the food is on the field. And I think we should turn on the robot. Yeah, turn on the robot. And so what we're doing right now, Steve is our main driver, and he is going to connect to the robot. Once the robot connects to the internet.
Okay, so while the teams are going to be doing this, I'm going to be basically connecting to the robots as well here and visualizing what the robot is thinking about and computing and things like that. So you'll see on the screen kind of live what the robot is thinking about. So yeah.
And just to give an update on what's happening, of course, during demo day, nothing works perfectly. Everyone here knows that. We had an issue connecting to the network. Each robot here is on a separate network. You see well, there's a little bit of feedback there, sorry. You see several routers around the room here, and looks like we're in, and the demo should be starting promptly.
So it seems like we just connected to the robot and we loaded the gene mapping, so the robot should be starting to run the lidar. And we're going to be able to see some of the feedback of the robot soon. Yeah, now we're good. Just give it a second. No problem.
In the meantime, to provide some kind of context to what's going on here today, this is the showcase of examples that were tested and true yesterday in a building on the engineering quad. This is the first time they've actually been able to test at VAIL in this center. The lighting changes a lot of things. A lot of teams were here at 10, 1, working on this consistently until very moment. And of course, it works swimmingly until you try and do it live. So the teams you see here have tested this, have been able to showcase to the TAs and the teaching staff how well their robots work. And we chose them out of merit. So we will be able to showcase here very soon. We're up and good? All right.
We're still waiting for the Arvis display. All right.
So
give
here,
it a second. So right now we don't know the whole map, and the robot is actually running autonomously. Those yellow dots that you see there, those are the places where the robot wants to go, where it thinks it has not explored. And as you see the frames moving, that's the robot. And those yellow points is where we want to go, because we are uncertain about what's there. And so, sorry.
So you see here that the robot just turned around. The reason it did that is because at the point that the robot was...
It's just this one. Yeah, it's hard to see right now, but on our screen you can see there's like a past set point that's green that's going to go to this dot at the bottom left corner. Oh, sorry. It's going towards this dot in the sort of bottom left corner right now. On our screen, there's actually a set point path that's running an A-star algorithm. So right now, what it's doing is it's chasing one frontier at a time and just constantly moving towards the closest frontier. There's a bit of a sort of delay on the map, so you might see some markers that are visualized here, but the robot doesn't see them when it's deciding where to go.
And so this is fully autonomous. No, there's nobody driving the robot in the other room. It's actually, we just press one button and it's running by itself. And he likes to play tricks on us, so.
Yeah, so what it's actually doing is it's generating, what you're seeing is like an occupancy grid that's being generated by our LiDAR. And the way we're detecting frontiers is we define a frontier as the boundary between free space and unexplored space. And we just kind of do some image processing as, so we treat the occupancy grid as an image and do some image processing and clustering to sort of identify those points in the image. So one of the challenges is if, with these low fences that have, picket fences that have holes in them, if it doesn't identify that as an occupied space, it could run pretty close to the fence.
So you're going to see up here, there's a coordinate system labeled broccoli at the top right side of the screen. That corresponds to the piece of broccoli that the robot just saw right there.
We got banana too.
Yeah, and there's the banana down at the bottom, which is going to be this one over here.
Yeah, and so if you don't see the frame, but you see the object, the robot didn't see it. So, uh-oh. So it's trying to localize itself. But we should be completing the whole grid soon. Yeah, as you can see, we're almost done with the map. And so hopefully, nice. So it's updating, there's no gray anymore.
Another thing is on the right, you see an actual feed from the camera mounted on the front of the robot. Not only does this kind of give you a better force perspective of what the robot sees while it's navigating, that's not our battery, no. You get to see the scale of the images that it's looking for when it sees apples and bananas and broccolis in the exploration phase for the delivery phase.
And so at this point, it seems like we have explored the whole map successfully. And that's fully autonomous with little assistance. Nah. Okay. It just doesn't know what to do once it completes everything. So with that, we just we're gonna move on to yes.
Doing a little victory dance. You can leave it.
Cool. So after the exploration phase, when the map is done, the teams have to take orders for delivery. So the next step will be giving the robot an order of, say, broccoli and a banana, and then hoping that the robot will then visit those spots. So let's see that.
All right, so both banana and broccoli have been commanded to the robot for delivery. And the robot should begin to progress into phase 2 of its plan, which is the delivery phase. So with the map fully known, now it should return to the objects that it's detected, pick them up, and complete its mission.
One of the challenges that you may be experiencing here is you can see how the LiDAR points in this map are like pretty sparse. So the LiDAR has trouble seeing the fence as an obstacle because of the areas they can see through the fence.
Can you pull out the link for me?
Yeah, picking up banana.
Yeah, so you have picked up.
Okay. So we just picked up the banana and what's going on?
Can you run it as a node?
There's no broccoli there. There's no broccoli there. I think it's potted planted out of broccoli. So the issue with the mission right now is obviously because of all of the green in the field. It has just successfully picked up broccoli, which it found when it smashed into the fence right into the set of plants. It's broccoli-esque looking, but it did recognize, marked it as broccoli in the map, you can see, and then after it picked up the banana frame, navigated toward the broccoli, picked it up, and is now going to home, which is the initial position the robot was kind of set at, launched from. So can you guys talk a little bit about, I know during your demo day you have implemented line following. Can you talk about how you implemented that and how that benefits your project?
Yeah, so fortunately it's not running right now, but for the lane following, we basically took a yellow color filter for the camera image, and then we did a projection on some bird's eye map view of the ground relative to camera frame. And from there, you basically block off the left side of the grid, and you snap the grid to the points to the grid of the A-star map, and you exact a high cost to those grids in order to passively push the A-star planning to the right side of the lane. So
we just finished.
Okay, cool. Yeah, and we just delivered, finished.
Yeah.
All right, so let's give them a round of applause.
All right, so if we have a quick second, we're just going to give it some nav goals. It'll follow with A-star just to demonstrate the lane following real quick.
I'm going to go over here so that you can see.
And one of the reasons why we're trying to do things separately, the second you put everything together, the robot overloads, and sometimes it doesn't know what to do, what prioritize, and so that's why it's difficult to integrate all the software at the same time. But as you can see on that screen, it's looking into the, well, I'm going to let Will explain this.
Yeah, so in the image screen, hopefully it will detect the yellow lanes, and I did a polyfit for that. And that's basically, yeah, the camera is not calibrated to this setting yet, but then you can see that it's kind of wiggling around. I do polyfits on that, like parabolas, for a sliding window, and then that gives you a really good iterative spatial resolution. So that's basically the lane following. Yeah. Okay. Yep.
Well, thank you guys. Here, we'll give you guys another round of applause. It's a great demonstration of line following. As you guys can see, obviously, your environment plays a huge impact on how you, oh my gosh, so much feedback. Yeah, it has so much of a stake in the success of your performance, because you tested that so well yesterday while the sun was perfectly set in the room and the lights were on, and as soon as you change to a new building with a new set of lights, you get to see just how difficult it is to keep the fidelity in your full stack. So with that being said, we can transition to our second team. We'll pull up your slide here. And if you guys want to get ready, get the robot in, battery ready to go, so you can launch your successful demo. 1 for 1, so that's good. That's a good track already. Minor fence moves, and that's good, but no one jumped out of the track or tipped over or rammed straight through a fence. A few stop signs were blown, but that's okay.
Well, they start with pretty tight. I forgot to teach about the stop sign.
All right, so Team Rosie, if we could have one person on your team come up and... Oh, Team Harlan, that's right. That's right. If we could have one member of your team come up and present while the rest of your team scrambles to make the best, most beautiful environment possible. We'd love to hear about your robot.
I'll take over. I can help too once I'm set up.
Hey everyone, we are Team Harlan. So in order to do this food delivery task, we have pretty much 4 tasks that we want to complete. So the first thing we do is, as we're mapping, we're following waypoints and generating the map as we go. But like the members of this team, our robot also gets really distracted by cute animals. So if Harlan sees a cute cat or a cute dog, like we have on this stick, he'll get distracted and just start following them around. But it's also really useful because if he gets in a sticky situation, we could lead him out of it and also use it to go around and map the environment. So as he's mapping, he's also detecting various food that we've placed around the map. And every time he detects like a banana or a donut or broccoli, he'll pin that location as a vendor location. And you see that we have some cool visualization in RViz, where every time he sees some food object, he's going to drop a sphere of the appropriate color. So we have that bananas are yellow, broccolis are green, and donuts are pink, given the pink sprinkles there. Then after he completely maps the entire field, he can receive orders that we sent to him for what he wants to pick up. And he'll travel to those in the order we tell him to and pick up the food objects. Another thing we've added for the visualization is that every time he picks up an object, he gets another little sphere, a smaller one of the same color that he'll then carry around his back. So just looking at RViz, you can tell what he's already picked up. Then after he's picked up all of the objects we've told him to pick up, he returns home and drops his food all off. Yeah, that's pretty much the flow of what's going on. How are we doing, guys?
Perfect. And as the rest of the team sets up their robot and connects to the network, SSH is in, a few questions on why you guys had the design decisions you used, why you ended up going with some of your unique features. Can you explain a little bit the alternatives to your cat stick and why your cat stick is actually a very sophisticated method of getting your robot out of trouble?
Sure. Well, first of all, the CNN that's running on this is really, really good at detecting cats. So it's really robust in that. And we're using the bounding box that we get from viewing everything with the camera, and we're doing a heuristic for distance instead of using any of the LiDAR data, because we find that sometimes that's a little bit spotty. But if we just use the coordinates of the bounding box, we find that it's really, really robust. Yeah.
Brilliant, yeah. So just to kind of also put into context, every team has a different jailbreak strategy where running into a fence, it's almost inevitable in this environment, especially because the lanes are very narrow and the LiDAR has a 0.5 meter detection range. So if you start off in a place and your map is a little unsure, you're almost bound to at least clip the corner of it. So some teams physically move their robots, others can remote in and teleoperate their robot, so using the keyboard on their ground station, just back up and turn the robot out of into a safe space. Others use waypoint navigation, where they drop a waypoint onto the map like this and they can navigate around, and some do it autonomously. This, I think, is a very elegant solution to that, where you don't have to physically pick up the robot, but use the sophistication of the hardware at hand to actually get out of jail free, which is quite smart, quite smart.
And we also think it gives him a little bit of personality, which we like.
This is very true.
I have a question. How many pictures of cats did you have to show to train it?
So we were actually given the CNN that detects cats, but we're sure that it was many, many, many pictures, given how he thinks that many things that aren't cats are cats, so.
This is true.
It's weirdly better at detecting cats than dogs.
Yes.
So we suspect that there's been some sort of
fascination with cats.
data on that side.
Everything is cat by default unless it's not cat.
Yeah.
The neural net model that was trained is ResNet 50 for most of these teams, I believe, all of them here today. And the data set is the COCO data set, which is all images trained, or images in context. So a blank picture of a banana actually doesn't work as well as a bunch of bananas in context. So if you just like put bananas on a table, it would do a better job at identifying that than a plain photo of a banana.
Yeah.
That's why you see donuts and sprinkles everywhere and bunches of bananas that are going bad and heads of broccoli. because it actually works really well in context and not as well out of context. So that's why using a picture of a cat is fairly easy, and the dog is a little harder because I think it's also trained on teddy bears and things that look similar to fluffy dogs. Cats are a little unique in that they can be picked up a little easier without that in context. But yeah, to answer that question.
Yeah. We've also had some issues with our food, like the bananas going brown and it being unable to detect them as bananas. So we've been having to do a lot of grocery runs to just keep the bananas fresh. So we'll be making some really nice banana bread this weekend. Yeah.
So you said that for distance detection, you're using the camera and a sort of distance heuristic there instead of a LiDAR.
Yes.
Is that just in the context of the cat?
It's just in the context of the cat. Oh, it's, so the question was, we're using a heuristic for detecting the cat, and if that's just for the cat stick or if it's also for the detection of the other objects.
Well, so when we detect the objects,
One second.
in our RViz world for the objects, we place the beacon for them where the robot is at the time, because that's where we want the robot to return to, right? We don't want it to just like hop in on the thing. And you could do the extra math and figure out where it is in front of you and then figure out where you need to be behind it, or you can just drop the pin where you actually want to be. And so that's what we use there. And there's not a necessary distance calculation. Versus for the cat, we actually need to kind of have an idea of where it is in front of us. So it's a different scenario.
Are you ready?
Yep.
Cool, so yeah, let's get started. Start the exploration phase.
Oh, what? Oh, yes, we also stop at stop signs because it is good to be safe when you're driving around.
So that's it, noticing the stop sign right there.
Yes. He stops a bit far from the stop sign, but better safe than sorry.
Crossing the intersection. And now we're going to go explore the banana.
So I want to. Are we going to cap?
That's the battery behind me. So let's make it not explode.
So we detected the banana.
And you'll notice, is that our,
Do you want to? Yeah.
Yeah, so after we detect the banana, it drops that yellow sphere there on the map so that it knows that's where the banana is.
Closer to it.
Yep.
So on the RViz it says, I'm distracted, following a cute animal. A little closer, yeah. So it's detecting
yeah, this
dogs
provides,
and
as we were talking about before, a convenient way of both exploring the map in times where the nav position is not doing what we'd like it to, as well as bringing it where we want and saving it from the fence.
Yeah, so the cat behaves like a service animal, so just in case you're...
And then I'm going toward the donut.
So just a refresher on what phase this is their exploration phase.
Okay,
so
it
the
got the donut.
The team right now is searching the map for food, adding it to their map. As you can see, from the beginning they had mentioned they had changed colors, so banana yellow, donut pink. And they will
I just have to
search more map, and when they are finished exploring, they will begin their phase 2, which is the delivery phase. And we hope that the team here, as they pick up the food item, will then, like they mentioned, carry a little dot with them telling you that it's been it's been collected. There's a battery has fallen out of the back of the robot, so there's going to be a little
storage for the batteries.
Yes.
Just gonna sit there. We're gonna be okay.
Beautiful.
Ooh, great.
Another caveat of the fences is that it likes to, even if you miss the fence perfectly, it will tug on something, and you may have a battery fall out of the back of your robot. So here they're approaching their final food item, which you can see in the image on the right. It's a live feed from their camera. They're looking at broccoli.
So we got broccoli.
Oh, the blue rectangle is the robot. Even though the robot is circular, we chose to use a rectangle so that it shows some sort of directionality of the movement.
And as you can see, the broccoli was detected. And I believe that is all of our food items.
Indeed.
Yes.
So we're going to go into retrieval mode. If all goes well, pick up the broccoli, then the donut, then the banana, and then go home.
All right, let's see phase 2.
So first we're going to switch to delivery mode.
Yep, it's waiting for delivery request. I can see it. It's just lagging.
Right, yeah, that's a little behind us. Cool, pretty good there. Yep. Send it in.
Now it's navigating broccoli.
So it's now navigating to broccoli. Could you guys mention how you decided to handle the requests that came in from the delivery and how you chose to, the order in which you picked up the items?
Yeah, sure. So we send the delivery request just as a string with all of the items separated by a comma because it was just really easy to then get that and parse it into an array of strings and send it to each location, which he just looks up the location when he gets the object. And
yeah, you'll notice we picked up our first object, which is now chilling on top of
And for the order in which we pick it up, he just takes the request and goes exactly in the order that we tell him to.
Perfect. So as it comes to the spot, it recognized the donut from initially. We should see, there's a little bit of a delay there. There we go.
And he will realign with the same pose in which he last saw the object. The object.
So
Yeah, sorry, I
it's
get
picking
distracted.
it up, and now he is going to banana.
After he turns a little bit.
Going to pick up banana.
There you go. It's a little off-roading.
Yeah, it happens. But that's where the excitement is, right? All right, well, we have an unplanned detour through the middle, so we'll see how this goes.
Yeah.
Uh-oh.
But
There's a...
A-star does as A-star wants, so.
Oh, they've not run into the fence, but their battery has picked the fence up with them. So they made that out scot-free. That was pretty impressive.
We're just rolling with the tail, and like, it's fine.
That is quite a wide robot now.
Oh, he might just knock over that stop sign, but we'll see. Oh, got it. I think
now
we
is
should
a
take
good time
this
to talk about the
opportunity
safety of operating with lipos.
to...
Don't do this at home. Also, don't do this in the next demos.
So he's picking up the bananas, and now he should deliver them back at home.
I saw on the map there that it looks like the broccoli and the donut were...
Ooh. Go ahead.
The broccoli and the donut, I noticed for a moment there they weren't on the robot. They were at some point right over there. Is that why it took the detour?
No, that was a delayed update on the RBIS.
Yes.
In our world, you would still find him.
Oh,
That battery really does
But
not.
now you can see the full chain of random objects on Highland.
Yes.
Idea stacking them up banana peel style, a la Mario Kart.
And he has delivered to home, and he's done.
So home is where we started the robot initially.
All right, let's give them a round of applause. Good job, guys. Successful delivery.
Thanks, everyone.
Gotta go back in there.
Poor guy. Poor battery. Poor guy. Sorry, buddy. Let's go.
All right. Well, thank you, everybody, for coming tonight. I also just wanted to take a quick moment during this break to say a special thank you to our judges. So Aaron from State Farm, thank you for joining us. Thank you. Kyle from Velodyne, thank you so much for coming. Stefano from Samsung, Patty from Intel, and Mark from SEI. Thank you so much for being our judges tonight.
Excellent. So as we prepare for our next group to go, can one member of the team come up and present their work? Brilliant.
Okay. Okay. I'll just wait till the slide is up. We're Team Rosie, Team 7.
All right, so we have to quickly upload match and upload that the team has worked on. We just want to make sure we can visualize it from our work ground station here that we're visualizing on the live stream and to all of you now. This team had a very interesting way of doing the actual mapping. You can see here, they'll explain later. But we did not have the files, so we kind of would have taken away from all of their glory, and it would have been quite boring for us to just give them, or give you guys the plain view of it. So Team Rosie, please take it away on what you guys did.
Yeah, sure. So hi, everybody. My name is Brian. My other teammates are Parastu, Sarah, Oscar, Matt, and Mimi. And just to give you a brief overview about what the unique aspect of our robot is, one of the main things that we try to focus on is visualization. So we wanted to make it incredibly clear for users of our robot where the foods are in the map. And this also greatly assisted us when we were debugging our robot during this AA274 final project. So what we did is we imported 3D models of different foods, and we can visualize that in ARVIS. So once the robot comes up to a food and detects its location, it's able to place a model of that food where that food actually is on the map itself. So this allows us to see whether or not we've actually picked up the food, and the fact that we have 3D models makes it incredibly clear exactly what foods we have on the map itself. Besides just visualizing the food, we also have markers that visualize the robot. So we have a 3D model of the turtlebot that we've superimposed on its actual location. So as the robot drives around on the map, you can see this model. In this case, from a top-down view, it looks like a circle that's pink. And we also have the trajectory of the robot, the past trajectory of the robot, visualized on ARVIS as well. So as our robot moves around, there are pink dots that follow it. And so we can see exactly where it's been in the past as well.
Brilliant. So right before we kind of start their demo, they're getting their environment set up. We allowed each team to have the flexibility on how they wanted to set up the environment and what items they wanted to detect, just because it's so fickle sometimes to get it to work just full stack anyway. Giving them the flexibility of, I have a set of images that work well for me, allows them to have the most success and most time for creativity in the rest of their project. So as they set up their images of bananas and donuts, we can kind of talk about some of the other work you guys have done. One thing of note that you guys won't be able to see in the live stream but can appreciate here is that every member of their team has a pin. Now, you guys really took to home the identity of your robot. You've decorated her, all of the robots. This addition from last year, if people are unaware, has a new processor on it called a Jetson from NVIDIA. This allows us to do a lot more on board. And in order to kind of pay homage to the Jetson, all of the robots are named after Jetson's characters, some way more obscure than others. So this is actually Rosie, the robot. They have decorated a rose on it, and all of their pins have homages to Rosie. So, I mean, just in the 10 weeks, almost 7 that they've been able to work with the robots, they've clearly taken to home just because how long they have spent with them and how much of a personality they do have. And there's still little chunks of broccoli and sprinkles around. So if anyone's hungry after the demo. All right, as we do final preparations, are we good to go on the side of the ground station? We're getting there. It's a process.
Looks like the robot's just being turned on and then has to connect to the network. So all of this stack is built on top of ROS, which is the robot operating system. And what this allows is basically a lot of different computing components that make up the Autonomy stack to live on different pieces of hardware. So we actually have 2 computers on the robot. We have the Jetson that Chris was talking about. We also have a Raspberry Pi that handles the camera. And the students are running on their VMs, on their laptops. And we've got another laptop here for the visualization. And all of that's on the same network. And through ROS, it's able to communicate and share all the data, share all the topics through a system of topics and subscribing to messages that are being sent from one node to another. So that's kind of what's going on. It does take a bit of time to set up and get everything connected, but should have that going soon.
Yeah, and before our robot is set up, I think we're actually in the clear. Am I? All right. All right, we'll be good to go. All right, so you guys should be seeing Rosie complete her 2-phase exploration and delivery. All All right, so can you guys, as this is booting up here, talk about how you have decided to do exploration and the delivery process?
Yeah, sure. So during this initial exploration phase, we do waypoint exploration. So we set a series of waypoints on the map, and then the robot goes to those waypoints. That allows us to get full coverage of the different areas of the map and be able to localize the food there. One of the unique aspects of our project, I think, is actually calculating the distance of the food. So what we're able to do is we use the LiDAR measurements in order to be able to calculate the distance of foods from our robot, and then we snap the location of the food to the nearest unoccupied cell in the occupancy grid that's created via SLAM and the G-mapping suite. So what we're able to do is actually place the marker location in the actual area where the food is, but then when we're going to actually get to the food itself, because we are able to move that location and store its location based off of the nearest free cell, our robot doesn't actually drive into any obstacles, or at least that's always the hope.
And just while you guys see me in the middle of the field here, I'm going to readjust the fences, because after every test they will get a little, they'll change just a little bit, and potentially just enough to snag onto a robot, so don't mind me in the middle of the... Yeah, exactly. Just random shuffling of fences might help. That's also a little messed up. Thank you.
And as mentioned during the previous presentation, we're also running the ResNet architecture in order to be able to classify the various foods. So, yeah.
So I notice here on your map, I believe this is the first group to have done this. Could you explain what the pink lines are, the pink dots?
Yes, I can say that. So those pink dots showcase the latest trajectory of the robot. So what we do is we show the past, 15 timestamps. Each marker is given when the robot has traversed an extra 0.1 meters or so. So if the robot is just idling one position, the markers, new markers are populated in the map. But as the robot actually moves in the map, those markers are dynamically removed and added in order to show how the robot is being traversing the map.
Unfortunately, it looks like their models that this team worked on is not working on our laptop here, so we're going to try to do a laptop swap so you can see them on the projector.
They are quite brilliant. Truly impressive to see an actual piece of broccoli and banana and turtlebot pop up on what is a rather simple map here. So yeah, as we said, in order to get those, that's why there was a bit of a delay in the beginning. In order to get those files to work properly on our system, we needed the actual models, the STL files, which were a bit more difficult when you have completely isolated networks from the internet, so you have to transfer via jump drive, which I haven't used in about 8 to 10 years maybe. It didn't get to work or test prior to this demo, so we're just going to take the HDMI out of our laptop and put it on one that's actually working. An added benefit of that, which we haven't been able to showcase here, in the live stream of the camera, if you have the actual image detecting node running, you'll be able to see the bounding boxes on the fruits and vegetables and donuts as they are seen. So you can tell with confidence, it'll tell you between 0 and 1 how confident you are in it recognizing something. So maybe if it sees that it could be broccoli 0.7 or teddy bear 0.4. They were allowed to play with the thresholds on what things were able to be recognized as. So don't recognize anything under maybe 30% confidence or 40% confidence. But luckily, using the COCO data set, there's enough of a disparity that you shouldn't see very similar items. I mean, broccoli, hopefully, if you're eating it properly, does not look anything like a donut, which does not look anything like a banana. So there's enough of a spread in that you can have confidence you're not going to misclassify something. Dog teddy bear is a bit of an outlier there, but you will be able to see that on their modified version.
Mm-hmm. Yeah, and just to add on to that, another unique aspect of our project is in how we update the location of food. So as our robot is moving, we can attain with greater certainty as we move closer the location of the food itself. So what we've done is, as the robot becomes more and more confident in the food location, it will actually update its marker location on the map with the STL 3D model. And if that confidence falls below the last highest confidence measure, it will not update. So the robot is always storing the most confident location that it believes the food is at.
Great, cool. So we're just going to swap the feed real quick.
Oh, viewers at home, this may look quite green and flashy, so if you're prone to flashing lights, please look away, here or there. Ooh.
I might need to reach, so does it reach?
And in a few seconds, we should see the screen of the ground control station on someone on their team. Oh, I didn't notice that Rosie also had a pin. That is adorable.
Oh, you might want to mirror screens if you can.
That is quite a cool background.
Yeah, sure.
So yeah, just to also go into the class a little bit more while we have some time here. Apoorv had mentioned that the use of ROS allows us to have multiple nodes on multiple different computers, kind of achieving the same goal. But the classes itself is modularized in a full stack frame. So students, over the course of what seems like the fastest 10 weeks ever, have to do full stack autonomy. And in that is included with like image detection, SLAM, path planning, optimal control. And there you go. You can actually see it's detecting a bunch of people. I forgot. People is definitely something it will be classifying, especially everyone in the crowd. There's a little bit of a delay between what you see here and what actually is shown. But you can see the nice broccoli model that they have uploaded and all of the smiling faces in the crowd. But this should give a better representation of what the robot sees. And this is something. The camera is something that is included in the baseline. So all the teams are able to use this as they debug. This team went above and beyond to actually make the visualization one step more real. So it has found all of our judges to be person, which is good. You passed the exam. No robot. No robots.
Okay.
So what seems to have potentially happened is the robot had wheeled up to the donut and classified a person, the location of the person as the location of the donut. So in fairness, we will not ask for donuts. I actually had a bunch of donuts yesterday, so I wouldn't want to order a donut for like the rest of my life. But it might have thought you were a donut. You know? it classified you as a person, but marked you as a donut. That's not gonna score well from the judges. But the issue caused with that is that if they were to actually go retrieve that donut, it looks like they're going for a second pass to update the location of the donut.
Don't move, judges.
Yes, everyone stay fully still. You can see it did classify donut with 75% confidence. That's quite high. And I think right now the hope is that they recognize and detect the object inside of their map, because if they go and retrieve that item, it will not be able to be retrieved.
We're
because
actually storing the location of the robot at the time, so
oh,
it should still be okay.
Brilliant. Well then, scratch that. So what they're doing is, in order to retrieve the object in their phase 2, they store the location of the robot. So as long as the robot was inside of the boundary, they're good to go.
So people wait here. That's a distraction over.
And it looks like we have also detected the banana. Is that 57% confidence? It is on the map. All right, so we have all of our food items. We can prepare for phase 2.
One question. So if you're, whenever you're storing the location of these foods and you're also storing the location of the robot, how can you be certain in every situation that like the location of the food will be the same as the location of the robot if you're just using the robot pose to go back and retrieve the food?
So that's a question on, correct me if I'm wrong, the difference between static detection and dynamic detection. So if you're detecting food and storing your location as the location of the robot, how can you be sure that the food is still there when your robot returns?
I guess if the food is not there, if the food is moved, then we wouldn't know either way, even if we stored the location of the food. So this just makes sure that we go back somewhere on the map that we're able to actually drive to. The dynamic detection will be a problem either way, I think.
Another one of the kind of assumptions given to the students for their task was that this was supposed to model kind of a farmer's market, where if you want to go to a farmer's market, sometimes you stroll up and down, see what's available, and then decide to make your purchases. So in this case, I don't think we actually alerted any of the students to the possibility of dynamic objects, more that they would be assumed to stay static the entire time, and that storing their robot location or the location of the food was a viable option.
Okay.
Assuming that the farmer's market didn't change their stand. I don't know if that happens. I need to go to more farmer's markets.
Cool, so can we, it looks like we've detected some objects, so can we switch to the delivery mode? Yeah.
Yeah.
Request the broccoli.
Yeah, so just to reiterate, so at this point we're going to try to request broccoli and then afterwards return back to our origin location, which is designated as home. So just to provide an update on what's going on right now, so in the past we've had significant troubles with our navigator module, so sometimes it crashes, which is why when we just try to send a goal pose just manually to get it to move, but obviously the robot hasn't moved, so we're going to try to kill that node and then reboot that up again. So that's been an issue that's somewhat plagued our robot.
And a lot of the teams that have presented to us yesterday, and I know when I took the class, there is kind of the working version of your robot has a very specific workflow. So a lot of teams not only have had to test the robot in its perfect state, but often test the robot in an imperfect state. So there's a lot of kind of hack engineering that goes on behind the scenes that you can't fully appreciate here, but the teams, despite being given quite a skeleton baseline, have had to kind of understand these this code base inside and out. So as you've seen here live, they have actually debugged their system, which is thoroughly impressive. I did not expect that thing to move ever again. I had faith in you guys, but this is following the laws of demo day. So hopefully here we can go succinctly into phase 2, which is of delivery, and actually pick up these food items from the vendors.
I think it's right into the fence.
Every group touches a fence. All right, so right now a request is being sent to pick up a banana. So we should be beginning phase 2 right now.
Looks like the banana might have disappeared from the map. Is that?
No, it's sent.
Is it there?
Sent the
Okay.
pose, but it's, yeah, you can see the goal. The goal is right here, but I can't get to it.
So the blue dot is
No, it's that the pose is sent outside of the map.
So has it placed all the items outside of the map? Is that the issue? Okay. Yes, so yeah, what it looks like it's happening is that it's placed the food items where it thought it saw them, but the map does update as we see more data. So it seems like here the map is updated in a way that the food items that the robot saw are now outside the reachable space of the map, and so that's giving the navigator some issues.
Like where exactly? Or can you ask like someone else to do it potentially? Okay, sure. Sounds good.
So team, while we debug the demo that's going on right here, could you kind of talk a little bit about the different path planning algorithms that you explored and why you ended up going with the one you did?
Yeah, sure. So two of the path planning algorithms that we were looking into in order to try to localize, or in order to get to target locations were A-star and then RRT. In our case, we decided to go with A-star just because it's a fairly robust algorithm, and the map that we knew a priori was going to be like a fairly simple map. So in this case, you can really think about the robot driving around as just navigating this 2D plane where you have certain obstacles that are in the way designated by the fences in the area that's within those fences. So using A-star and then having an occupancy grid where we use the G-mapping suite to transform LiDAR points to areas to be avoided proved to be a fairly robust solution. Additionally, one of the things that we tried to implement as well in order to try to reduce collisions with obstacles is like sort of somewhat inflating the sizes of the obstacles. So when we get the data that's coming from SLAM, what we do is we slightly inflate those sizes, and so as a result, the robot has less of a chance to try to collide with different obstacles as well. We also tune the velocities of our robot a bit, so sometimes the robot has a somewhat high inertia, so when it gets close, it's trying to be very aggressive with turns. That can sometimes prove to be an issue. So we try to mitigate that, but of course, things never go exactly to plan, I suppose.
If you're inflating the size of the obstacles in the occupancy grid, would you ever foresee a situation where maybe you run into a path that was maybe really narrow, but your robot decides not to take it because the occupancy grid was inflated to the point where it blocks it completely?
Yeah, so we definitely saw that behavior when we were originally just going through. So for example, this central corridor here is quite narrow. So if you inflate the obstacles too much, then obviously, the robot did have difficulty and would sometimes take much more circuitous routes. So as a result, the amount of inflation that we're actually using is quite small in order to accommodate that. Because, like you said, that was an issue when if you inflate the size of the obstacles too much, then the A-star planning algorithm just sort of throws up his hands and says, "Oh, I can't actually find a clear path." Mm-hmm.
Cool, so it looks like they've seen the banana, so we're going to try this delivery one more time. One more shot, and then go on to the next team.
Yeah, I think it might have hold it. It might have placed an obstacle there.
All right, so it looks like we're going to move on to our next group. If we could have a round of applause for Team Rosie. All right, and as we prepare for the next team, could one member of their team come up and present their slides? Sean, you can do it. All right, so we're going to be moving on to Team Cogswell. Again, following the Jetsons theme. For the few here that are kind of still remembering the Jetsons, probably not even half. Yeah, so that's a good question. So you can see the robot here has a lot going on in a very condensed puck. So it's actually a bit more, I would say, beefy than it was last year in adding the Jetson. But we have the Velodyne LiDAR. We're using the TurtleBot 3 system as the base frame of it, which has wheel encoders and an IMU in a they're placing the robot in a power board, and then you have a Velodyne system, or no, a LiDAR system on top. We've gone with Velodyne for multiple reasons. The choice of actually going with the Velodyne predates me. Apoorv, maybe you could talk a little bit about why we've actually chosen the Raspberry Pi setup and the Velodyne that we did for we're getting very extreme feedback. We can't be near each other. Why we had the hardware decisions we did in particular about 2 years ago.
Sure, yeah, so I can speak a bit about that. So, so the TurtleBot package is, starts out as like a nice compact base system to do all sorts of kind of robotic demos. Has everything from a camera to the control board for the motors and a small laser scanner. But to make the project more realistic and to, through a generous donation from Velodyne, they gave us a lot of these LiDARs. We have the same LiDArs that are used in autonomous vehicles. And so that's why we upgraded the cheap laser scanner that was on the base TurtleBot with the LiDARs from Velodyne. And so it's giving us a lot of data that in more than just the single plane, which is pretty cool. As far as the camera, it's we're just using a standard Raspberry Pi camera, and so that's why we have the Raspberry Pi as well as the Raspberry Pi camera. Yeah.
Yeah, several opportunities kind of early this quarter. The reason we have both the Raspberry Pi and the Jetson kind of fell from the fact that last year we were doing everything on the Raspberry Pi. And since it's a powerful machine for its size, but it's not powerful enough to run everything on board, including what you see here, which is the image processing, the neural net, G mapping, doing everything. We had to port a lot of it over the network, do it on our laptops and send it back. And just the load of that caused such a delay that when you're relying on kind of almost real-time navigation and SLAM packages, that if you have a huge latency, your robot is going to not know where it is and collide into things way more frequently. So we beefed up with the Jetson and kept the Raspberry Pi because we didn't want to have to get a new camera and just increase the cost of the cheap system that we have here. And cheap is with gigantic air quotes because it is a robotic system. And the decisions we made kind of were not easy, but it does what it needs to do. This is a vast improvement in terms of how quickly we can run these things to last year and how much more fidelity we can get. The teams this year were given kind of a suite of creative options as a result of having the capability of both the Pi and the Jetson. So as a setup, it's quite robust. Hey, that's a good question. Thank you.
Do you imagine the limit on onboard computing being true for like real cars?
So the question was, do I imagine the limit of onboard computing being true to real cars? I think that in many ways this is a fantastic analogy to what's out there in the field, not only in terms of hardware, but just in terms of the environment itself. I mean, the environment is set up in a way that it's supposed to mirror the autonomous driving scenario. So you do get to see, we're using kind of COTS systems here, commercial off-the-shelf Velodyne. You can test these and have your trial and error scenarios and then perfect it and go to a new facility such as this, which you would think the lighting is perfect for a demonstration like this, and there's panic. So every time we go to test something, we find a new challenge, right? A new feature that we have to adjust for. So I mean, with greater computational ability comes greater flexibility to improve. So there's always going to be computational issues on any system you have, and I think given the scale of what we have, it's a perfect scale of the computational complexity you would see in real life.
Yeah, I was just wondering because if off-board computing is going to be something that is going to happen in the real world, then this could be really good skills to figure out how do you manage all of that.
Yeah. So then, well, are we prepared for Cogswell? All right, we're ready for Cogswell. I will come back to that question when they are finished their presentation. It's a good one.
All right. Hello, everyone. So I'm Sean. I'm here with Team Cogswell. We have Andrew, Jaron, and Tane here. And so for our project, we focused on an autonomous exploration of the map using a frontier-based search method like one of the other teams here. So if you look at this figure in the bottom left of our PowerPoint slide, you can see a red dot. That would resemble the Totobot's starting position. And the light blue area is region that it knows is free to drive into, while the yellow is known obstacles. And everything blue is unknown. That's the unexplored area. So our Totobot uses this information to pick a desired goal spot that's the farthest away from it, using a buffer zone of about, what was it, like 20 centimeters or so of all free space, and it uses that spot as its waypoint goal to drive to. And upon reaching that point, it does the same search again, but excluding the current part of the map that has been visited. So we're looking at the new free space to drive into. Upon seeing obstacles in our RViz viewer model, we will leave a landmark where we were when we saw it that we can return to later by entering a delivery command. And yeah, that's most of what we have. We enter delivery command by either seeing the entire map when there's no more frontiers. We'll begin to return home unless we give a delivery command. Or at any point, we enter a delivery command, it'll switch out of exploration mode and return to that object. And if needed later, we can always re-enter exploration mode to continue exploring the map. We also have a few things that if the Turtlebot gets stuck, we have a reset mode that will help just move its position around a little bit to hopefully have it relocalize in the map to continue driving. And a manual mode that we can give it a manual waypoint to drive it there to a known spot. So, and we're going to start our demo. Thank you.
To restart our race when
yeah. Okay. So do you have that yellow mark?
All right, so we're waiting here for our system to boot. And that was such a quick wait. And now we should be entering phase 1 exploration. As Sean of Cogswell had mentioned, they are doing autonomous exploration and delivery. Amazing. As you can see here, it saw a stop sign, went into stop, and then cross mode. It's a bit early, but it did stop. It did stop. You might still get a ticket, but ethically you're there. So now we're approaching a fence. Oh. There we go. All right, so this is actually going to be a very interesting demonstration of what happens when you have an off-centered LiDAR. As you can see on their map here, when their robot drove up on the side of the fence, it populated points above the boundary. So now it thinks that the map is a lot more free than it actually is. I believe this actually happened to us last year. This might be the curse of the second-year Aeroastro team. I know all these guys. Yeah, this is like identical to us. So, as you can see on the demonstration, they just believe they drove directly through the fencing. And as a bit of context here, the risk in doing a demonstration that is fully autonomous in exploration before you have a known map is a great one. And I don't want to make light of the fact that it is only marginally easier to go from teleoping to waypoint navigation to autonomous exploration. These are huge gaps. Teleoperation means you have full control. You control your speed. You control what you see at what time, and you know whether or not you're going to hit a fence. Waypoint puts you in the kind of unknown of your controller. So if you say, I want to go to this point, now it's relying on your controller to get you to that point. But as soon as you go into a full stack autonomous exploration phase, you have no control. So as you saw there, they had just that one blip where they bumped into the fence and tilted the LiDAR a little bit, and everything was now in complete unknown space. So these are huge, huge risks and huge gaps, just to, again, stress the complexity of doing this fully autonomous exploration phase. I believe they're doing a quick restart, just hoping this time it doesn't tilt onto a map to kind of show you the full capability of what they've done here, which is no small feat. but it does. This is a perfect showcase of just how sensitive full autonomy is and why you should just be extremely cautious, even if you think you don't have to be. So it looks like they've reinitialized their robot. Can you talk about the initialization process? You guys have a very unique flow of how you do the phases.
So as you see, right around where the TurtleBot currently is, there's roughly a circle that's 1/2 meter in diameter. So when the TurtleBot was turning on, our LiDAR was having a tough time figuring out exactly what was next to it, so it might have hit a couple obstacles. So upon startup, our TurtleBot moves forward a little bit just to try to get to see part of that area so it can avoid obstacles that are right next to it at the start. And then after some time, we enter exploration mode.
Yeah, and to kind of reiterate, upon initialization of the LiDAR, there's a 1/2 meter gap of information. So what they do is they drive out of that 1/2 meter to repopulate the unknown, and they do that in a safe, linear manner. So this does require them starting in a position where they can drive forward, but is a good and creative way to get around a hardware constraint.
Yeah, and just to reiterate, the LiDARs that we're using are the same LiDARs you would use on a real autonomous vehicle. Obviously, the environment that we're putting them in is much smaller scale, so there's a bit of a mismatch there, which is why there's this kind of gap between the robot and what it can see, detect with the LiDAR.
Exactly. 1/2 meter is nothing when you're mounting it on a car and you're looking for a stop sign several meters in front of you, but if all of your fences are 0.2 meters around you, then you have to be much more cautious on initial setup because you have no idea where you are. You just know where the things are far away from you. Yeah.
I have a question. Why, in this case, it seems that the points forming the clusters of objects are more, there's less points there. Can you repeat the question? Yeah, there are less points there.
Yeah, so his question is why, here, I can actually pass him a microphone.
In this case, it seems to me that there are less points detected in the point cloud of the LiDAR. Is there a filter or something that filters out the points coming from the LiDAR?
Can one of you guys address the question? Sure.
So the question was, is there something that filters out the LiDAR points? So we have not implemented anything different than the base LiDAR package. So I'm not aware of anything being filtering.
So maybe the question was about the resolution of the grid here, or?
Yeah, in the other cases you have, they had more points, were quicker to get points where you find the fences or the other trees. I don't know why in your case, maybe it's your frontier approach that limits the creation of their geometry.
Oh, perhaps it may be our speed. Maybe we're a little faster than the other robots, so it takes longer to update the map. That may be the case.
Yeah, that's a very good observation. The speed of the robot is something that the teams really only get to test near the latter end of the quarter. As they fully have developed their full stack autonomy, their full stack system, they get to test it in this environment in particular, not just anything they can build with boxes. And the speed of the system is crucial to how quickly you can pick things up and the fidelity of your control. The teams typically go at an absolute crawl, and especially as you jump further and further into full autonomy. So yeah, the fidelity of this is probably, I would say with some certainty, that it's the result of them moving faster than the other teams.
So we had to reinitialize the simulation. So right now we're trying to go back into explore mode. So that's what you saw was the initialization phase. So now it should pick a new frontier, which you can see as the green line. So it's picking the farthest frontier with a buffer zone. So we don't want to pick a frontier that's right on the edge of the wall. So we have it so that it's far away from for the known obstacles. So hopefully this time it'll be a little better. So it's in stop sign, solid stop sign right now. The markers, as you can see, they're tall cylinders. Those are where it saw the respective obstacles.
I think you guys were one of the few groups to actually visualize stop signs. Not only respect the rules of the stop sign on the road, but visualize them so that you can see on the map where there are these points that you should be stopping.
Right, so as you can see, the red marker is for the stop sign, the blue is for the water bottle. And then as the yellow dots behind it are the trail that it has, the trajectory it has traveled so far.
And just to reiterate again, this team is doing autonomous frontier exploration. So they haven't set waypoints. They haven't been compelling the robot to move in a certain direction via their keyboard. It's making these decisions as a result of their algorithm, and they really have no say in what's happening, which is impressive but dangerous. So it looks like the map's fully explored. There are some gaps over here, which will be interesting to see in the fencing. You can see it's picking up some of the points in the fencing right now. It has. Is it in cross mode? It did. It stopped in the stop sign and has gone into cross mode. It's a weird position of a stop sign. You wouldn't really see that on the road, on the wrong side of the street in the intersection. But it obeyed it, so I guess as the driver, it's all you can ask for. And it looks like, despite it, you can see the path that it planned on the screen here and decided it was going to take a trip through the park. And yeah, as Professor has said right now, the fun, I guess, caveat of using a high-fidelity LiDAR system like the Velodyne one here and gridded fences is that sometimes you do get beams that go through the fence. So you don't actually pick up your environment with 100% accuracy as a unplannable space. It was well filled, yeah. That was definitely an anomaly because it's planned its path already. Yeah, or control, right? As it's, yeah. All right, I think we should move on to our final team. I think we're quick on time here. Yep. All right. So as our final team, let's give Cogswell a round of applause here. They took the ultimate risk, and it paid off yesterday. That's why they're here. It was phenomenal yesterday, and of course today, of all days, it decided to run into every fence possible. But congratulations, Cogswell. Huge risk. That's why you guys are in this class. So.
Why do you think such a high variability between yesterday and today? Because this is mostly LiDAR-based.
So yeah, the difference between what happened yesterday and what happened today is kind of up in the air. You can run a system once, especially as you become fully autonomous. You can run a system once, and then 3 seconds later run it again with completely different behavior. So it may have been luck of the draw yesterday. It may have been bad luck today. Either way, yep, you guys are up. Either way, they did have a system that worked, and today just on their demos it decided not to. All right, so our final team. Slides are cut off. Yeah, I'm going to fix the environment.
You ready? Yeah, let's run it.
Do you have music?
I have an issue.
Oh, use mine. Oh, okay, yeah. Use yours. So we'll just go switch to it.
Well, I don't know. I've never tried running one. I've just
You do have the bar, right?
Is the robot on?
So I should do it now. No, it's no power. Object setting. Battery. Or battery.
So as you're setting up,
Robot
does someone
ready.
want to do the slides?
Robot ready?
Okay.
Yeah, it's fine. All right, you keep doing the checklist.
Cool.
Should I give the presentation?
Yeah.
And then, but we're still setting up.
Just while you're setting up, unless you need to be setting up.
That's fine. What do you want?
Are we
Set up
done
our
setting
viz? I'll do our viz for you.
Can you set up
yeah,
this
I'll
on
do
my
it.
computer?
Yeah. Let me just log into the
Okay.
first. You go to do the presentation.
I'll do this then.
Cool. Yeah. All right, guys. Let's hear from Team Rudy.
Hello. Okay. Well, hi. I'm Nikhil. I'm part of Team 5. We are the Rudy team. And a theme for our project is that we wanted to build as many systems as possible to make sure that our robot could run as robustly as possible. So to that end, we started with the brain of our robot, which is the state machine, and we refactored the state machine so it would use an object-oriented state pattern, which allows us to really easily and modularly decompose the logic for what was going on in the robot. So that was the first edition. For motion planning, we created an augmented occupancy grid, which basically encourages safer motion by adding, for instance, buffers from the wall and other features. You can imagine, in some next stage, adding like grid, some sort of cost function for grids, so it weights particular locations of the road more heavily. For object localization, we implemented an algorithm that would make it such that the more samples of the objects you would get, the more accurately. So we implemented an EKF to basically collect more samples of object position and try to get a really robust placement. And you'll see the placement of the different objects show up in our, because we have different markers in different colors that will show up. And then finally, we optimized our pose controller for this hardware so that it turns in place and moves. And this we found allows for cleaner motions. Hopefully no cutting through corners, though we'll see. And that's it.
Brilliant. So this is our last group, and we hope that it is a successful demonstration. You've seen the full scale of what's happening in the past 10 weeks. Realistically, all of the hours that were put in the last 2 to make all of this happen. The students, I believe, hopefully have slept and showered since they first entered skilling like 72 hours ago for the crunch time of the project. But we've seen them run, we've seen them not run, and Rudy is definitely last but not least in the capability of what they're presenting today. You can see it's a slide full of extra features that we asked them to be creative with, and they really delivered. So hopefully here in a few seconds we can get Rudy up and running.
Yeah, there's just some issues on with setting up their RViz thing on our computer, so we're going to be using their computer for this, which is what we're setting up right now. But should be set up in 1 second.
Yeah, like with the group that had the 3D models of their foods, it's a little harder to get the exact copy of what they're doing on their laptop over onto ours for demonstration, especially if we're on a network with no internet. So we're just going to take their laptop and use that to visualize for this final demo. And then we will be free to eat. I know that's why most of you guys are coming. Not you guys are here for the good stuff. I could eat. But one final demo, and we'll be good to go. Yeah, so if a member of Rudy could be available for questions, could you guys talk about how you decided to do both phases via either waypoint or autonomous navigation?
You guys said the same.
We're good to present.
I think we're good.
Yeah.
You're good?
Yeah.
All right.
But what was the question?
For the phase 1 and phase 2, can you talk about whether or not you did waypoint navigation or autonomous exploration, or what you decided to end up as your final architecture?
Yeah. So we chose waypoint navigation to start.
Inspiration. Again, good background.
Thank you. Thank you. Here, Warren, can you actually talk about this? I'm gonna debug this.
No, it's just that we're just not showing the VR.
Well, we chose waypoint navigation just because I guess it's the simplest so far. I mean, there's other things that we're trying to bring up ultimately. But I definitely do think autonomous mode probably would have been if we had a couple more days, probably would be also within reach to bring up.
Brilliant.
I have a question. So for your control system, you said you're just simplifying it to rotation and then moving.
Yeah, because we noticed that motion actually helps move around the corners much better than the original pose controller that we started with. The original pose controller that we were using was a control function, and we noticed that it would actually move in a curved, splined fashion, which we felt wasn't optimal for the turning in this environment that we were testing in.
Do you feel as if there might have been any speed deficiencies compared to other teams when just using this stripped-down control system as opposed to...
Sorry, could you repeat that?
Do you feel that there might have been any speed deficiencies compared to... Wait, you might be sacrificing on the speed?
That is true, yeah.
Sacrificing return.
Yeah, ultimately, you know, when we're moving, we're not turning and moving at the same time. We're only doing one or the other. So it does go a little more slowly to the actual final pose. But, you know, for us, I guess the motion and the accuracy in the path probably meant more to us. Like, not actually, we were concerned about if we had the original implementation that it could move in a fashion that could hit, you know, a fence or something like that. So for this method, we felt like it was more accurate overall.
And for context, a lot of these fences have been reprinted since yesterday because the frustration of hitting a fence is real. A lot of teams hit fences and you just roll them over. They were so mangled by the end of yesterday that a lot of these are actually brand new. The ones that are disconnected especially have just been laser cut out. And you can tell that the design decisions by some of these teams have been not around autonomy, but around feasibility and frustration, right? You have your hardware limits and you have your hardware constraints as well. So teams have decided to simplify their control to hit less fences because it may have been slower, but it's a much more reliable route.
Yeah, and as you'll see from our demonstration as well, its movement around the current corners are pretty smooth. So
that is a TurtleBot. Can you talk about how you went into your visualization models more?
Sure. Yeah, so we used a robot model, a demonstration to visualize the TurtleBot. It should follow as we move the TurtleBot around. There's a cube as well to help with visualization just because it's gray on the gray background. But we should see different colored cubes pop up correlating to the different objects that we see. And so, for example, broccoli should be green. If we get to the bananas, it should be yellow. Just to help us visualize. And you will see the original position shown with the map axes.
All right, I think we're ready to go.
All right. Our final team, let's begin phase 1.
Cool. Let me zoom out of this ARVIS first so everyone can see what's going on. So now we started off with not knowing a lot about the state, but we'll slowly explore and see the stuff. So every time we see an object popped up, we will have the visualization on the ARVIS. So we are trying to see banana. Let's see if we see the banana yet. So here's a view of what the camera is seeing. If we detected an object, we will see a bounding box and tell us what's the confidence it is with the object detection.
Yeah, we're going to come back here just because the banana's angled.
I can.
The wind is kind of blowing.
Well, yeah, a back group, yeah. Okay, well, I guess we're looking at a donut now instead. Cool. Okay, so continue about what Nikhil talked about our state machine. Here we have a Ross topic echo about state machine. So we can switch state machine very easily and also visualize what state we are very easily. This actually helps us a lot during debugging because basically our architecture is very modularized. We can easily use a supervisor node to change any state, switching from manual state to the actual navigation state. And here we saw the donut, and this is the location that we marked down at the map. And it looks like they also think the donut is an apple. So, I mean, they're kind of similar. They're all like dessert, all right? So, acceptable.
Identical nutritional value.
Yeah, totally. But yeah. Oh, okay, yeah. So let's see. Oh, sorry, this is very hard to scroll.
We are macro zoomed in. There we go.
There you go. Okay. So, okay, so it looks like we just found a broccoli. There you go. So maybe we can, let's explore it a little bit, and then we can start our food delivery.
So can you talk a little bit more about how you're getting the distance of the broccoli to be there despite being quite far away?
Yeah, for sure. Yeah, the distance only based on based on the LiDAR. So LiDAR see a scan point of where the bounding box is, and we pretty much use the average across the bounding box of the distance to use that as a distance. So we definitely know that this is a very noisy representation of where the distance is. So to get a more accurate estimate, we implemented like a very simple EKF filter to filter out the correct location of the broccoli. So it looks like we are getting a pretty good estimation right now because the object is just staying static and not moving. But during testing, actually during our demo yesterday, it was actually moving quite a bit because for some reason the LiDAR isn't giving out a very clean signals. But yeah, so that really helps a lot.
One of those rare cases where things work better on the demo day, right?
Yeah, so far this actually works better than yesterday. So far, we'll see.
Yeah, you might have just jinxed it. You broke the one rule.
Wait, what happened? Okay. Don't scare me. Cool.
So I don't know if we've actually mentioned this, but the view on top of the live stream is a view from a GoPro camera that we have mounted kind of diagonally in front of the screen or in front of the environment. And I don't know if many teams have actually traversed this leg, but here you get a really good sense of what the robot looks like and kind of the pacing in which it moves around in the environment and the scale with respect to its surroundings. As we round this corner here, we will be looking at this set of bananas, probably. If you need me to hold them.
We're going to request, but we can also.
Yeah.
Okay, yeah, no, that's actually better. So let's, Apoorv, do you have an idea of what you want to get from the farmer's market?
Yeah, what do you want?
You've got...
Nikhil, let me know, what do you want to eat tonight?
Broccoli and donuts. It's a huge,
let's do broccoli first, and then we can maybe pick up donut afterward. Gotta be healthy. So, I'll do that. So here we can, so to switch state, we'll just do state machine, and then we'll change the state to state request. I noticed the resolution is kind of low here, but all I'm typing is just state machine _ request. That will public a message to the ROS node, and it should see it. And then here you can see that our log, the state machine said that it goes from manual mode to entering request mode. So now we can type in a request. Can you request it, actually? Yeah. It's right there. Okay. But yeah. So Nikhil entered that he wants, think broccoli. All right. Oh, sorry. My bad. Cool. Is it running?
Yeah. It's computing. It's computing.
Okay.
It's gonna
map too. Okay.
All right, so it looks like the request for broccoli has been
Should we show?
sent out.
Here, by the way, here's the augmented occupancy grid. So you can see, this is what our robot is planning of the world, and it's the features it's added. So I can close it.
So a nice off-camera flex right there from the last team was that and off mic, no one at home will know the work that you guys put into that. Maybe I should just say nothing. No. The work that they did was they actually post-processed the map, the points that they recognized as obstacles, and inflated them a little to get a higher fidelity map of a high confidence. And it actually looks quite good. Probably one of the best that we've seen definitely this year, and I've seen in the past too.
Because the map seems clear enough to just the bounding geometry drawing out of the points.
Yeah, so that's a good question. I'll pose to you guys. So why did you guys end up deciding to augment the map as compared to just using the map that's here that you do get to see kind of a lower?
Just the bounding geometry. So I imagine that this is more extensible because then we can add our own features. And then as I was saying, like if we were to want to do, say, lane following, the first thing I'd do is I'd overlay some sort of cost function on top of this map where the cost of a particular location like encourages following the right lane, like not moving down the middle of the road. Because right now it'll move anywhere. But by developing our own representation, we can add more things.
Get a more higher resolution map. If you wanted to overlay more particular things that you wouldn't be able to do with this map representation up here, and that's why.
Okay. So can you tell them what's going on? Yeah, tell them that.
Okay, so here we have an issue right now because as you guys can see, there's the broccoli is kind of surrounded by the object. So the A-star couldn't find it because broccoli was kind of in the wall. So we try to resolve it, but there's a threshold of like how much. So basically how we resolve this is we do a BFS of trying to find the nearest free neighbor of where the object is. What do you want?
Oh, can you put it back? So basically we're going to go to donuts. Yeah.
We all want a donut anyway. No one really wanted broccoli. So.
Oh, sorry.
Yeah, that's another one of the trade-offs in allowing people to use their own objects. Depending on how you represent your objects, you could be representing something as a goal position, or you could kind of inversely or kind of, I guess, unintuitively be representing it as an obstacle. The more kind of depth your object has, the more it'll get picked up by the LiDAR and be viewed as an obstacle and a goal, which when you're doing path planning, saying take me to this point, there may not be a path that's being able to be planned because you have now classified it as an obstacle. So a lot of teams have had to kind of discover this on their own and then come up with their unique solution. And this team has a nearest neighbor resolution to this, which just because of its location and the density of the points, it's actually easier just to choose a point like donut that is a little bit more free.
Where does it go to now? Oh, going home. Oh, JK. We go home first. That's fine. I'll tell them. Yeah, so basically we accidentally skipped a state. Actually, no, it's more like we requested a donut, but we forgot to put it back to a manual first to reset the request mode. So actually earlier, so we have the setting where once you request a food, you pick up the food and then you go back home. So now actually we're actually just going back home, which is now it's navigating back to home. If you guys can see, there's a green path on the very thin green line on the map, and that's a path that we just planned. So we're going home even though there's no broccoli, but that's good. So we can automatically go home. The function for going home is basically the same as picking up food, so that works too.
All right.
Cool.
Can you talk about how you're following this path, like how your robot decides where it's going and how to control its velocities as it tries to track this path?
Yeah, for sure. Okay, so first off, let's go back to how the path is computed. So the path is computed based on the map that Nikhil just showed us, the occupancy grid, and then we use the A-star algorithm to search it. So the path that's returned is actually returned back to the supervisor, and then the supervisor is publishing, that's fine, they're publishing each step to the post controller and to navigate back. So we actually thought about having a two different post controller or like post controller setting so that in the navigation mode it moves faster because each step is kind of small and you guys can see it's moving kind of like step by step right now. It's slightly slow, but we ended up not tuning that because we didn't have that much time to tune the parameters, so it's actually just using the same pose controller. But yeah. Cool. It's getting there. Yeah. Did you talk about how the wall is expanded? A little bit. Okay. Yeah, and then to avoid bumping into walls, the way we did it, I think Nikhil mentioned it, is that we make sure that each obstacle has a clearance, like a buffer boundary that the robot don't get to. And so that's how we're avoiding the fence. Okay, cool. It's getting there.
So just so I understand, when you're path planning, you're just giving those instructions to the robot. You're just giving a series of waypoints that will move to point by point, and that's why it's sort of, I guess,
yeah.
piecewise in its actual execution, that instead of just continuously driving from one point to sort of the end.
Actually, in fact, the object location doesn't have to do with our waypoints. So we could have observed that object from anywhere, but it is trying to place the object location on the map.
He's asking whether the path. Are you asking whether the path is broken down into each waypoint and it's navigated? Yes, that's how we navigate right now.
Oh, sorry, I misunderstood. Yeah, so it is breaking the path up into a bunch of waypoints. Yeah.
Oh, okay.
Oh, and it's
Cool.
it's seen banana too.
Yeah, that's good.
Cool. Looks like it's the final stretch.
Yeah, final stretch.
Will it make it around this last corner? Let's see.
I think we should.
It's not a very suspenseful event, but but if there were suspense, it would be now.
Yeah.
Yes, exactly. Yeah, slow but safe.
I'm just hoping it doesn't enter into battering ram mode and start hitting the wall.
Play the Jaws theme whenever you get close to the fence.
Okay, I think that's
Cool. Yeah,
All right.
I think we're go home. We're home. Awesome.
Cool. Let's have a round of applause for our team.
I think let's also have one other round of applause for all the teams today. All did a fantastic job. Thank you.
All right, now I think we're going to, as we kind of pass over to the next place here, have some closing remarks.
Yes, and we're just going to gather with the judges for the next couple of minutes to declare the winner. In the meantime, the dinner is ready. We are going to declare the winner very soon.